Okay, guys, here let's see types of pre-stressing of concrete. In the previous video, I just talked about concentric and eccentric pre-stressing. Here, let me introduce you first with the concentric pre-stressing again. A simply supported rectangular beam subjected to concentrated pre-stressing force. Here you can see pre-stressing compressive force F is equal to minus P by AC, where AC is the cross-section area of the beam. Okay, a minus sign is for compression, as you know. Let's move further. Here you see we already discussed in the part one of types of pre-stressing of concrete. Uh, we see that this is a uniform stresses that produced due to the concentric pre-stressing force concentrated to a line of action of a neutral axis, and this is and the second part is stresses due to the external loading. Okay, this was the basic concept. uh, Basically we need eccentric pre-stressing for the beams or girders used in bridges, where we need eccentric pre-stressing. So here is the answer. In concentric pre-stressing, the pre-stressing tendon is placed at the neutral axis. Yes, definitely. This step creates a uniform compressive stress throughout the beam. Yes, definitely. However, since the top fiber are already under the compression from pre-stressing force, applying an external load further increase the compressive stress at the top fiber. Uh, in this discussion, you can clearly see that when concentric pre-stressing is applied, the top fiber is in compression and the bottom fiber is also in compression. As we say, in concentric pre-stressing, there is uniform stresses across the cross section. So when the top fiber is in compression in concentric pre-stressing, and after the load is applied, external load is applied, then this applied load also cause compressive stresses on top fiber. So the top fiber will experience a lot of compressive stresses, both due to concentric pre-stressing and external load. So the top fiber will lead to cracking at top fibers. Here you can see this combination can potentially reduce the beam's capacity to carry the additional external loads, as too much compressive stresses can lead to crushing at top fiber. So that's why we uh, we we need eccentric pre-stressing to 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 avoid this kind of failure due to concentric pre-stressing. So eccentric, what happened in eccentric pre-stressing? In eccentric pre-stressing, when tendon placed below the neutral axis, there is a little bit tensile stresses produced in the top fiber, and a compressive stresses produced in the bottom fiber. Uh, so this is due to moment creation. Uh, let me explain it to you. To improve the beam's ability to resist the external loads, the pre-stressing tendon is placed eccentrically, okay, below the neutral axis at midspan. When the tendon is placed at eccentricity E from the CGC line, it creates a moment. In previous video, we clearly see that when the tendon is placed at a distance E from the neutral axis, it creates a moment that is PE. Okay, where P is the pre-stressing force. The eccentricity induces movement, and the movement generates a tensile stress at top fiber and compressive stresses at bottom fiber due to pre-stressing, or we can say eccentric pre-stressing, which counteracts the effects of the bending moment caused by external loadings. This is the important sentence here. As a result, the beam can take on a higher load without reaching the compressive stress limit at the top fiber, effectively increase the load carrying capacity. Effects of eccentric precessing at supports. As the precessing force is applied, if the tendon is located below the neutral axis, it creates an upward movement due to the eccentricity. These upward movements help us to counter the compressive stresses produced due to external load at top and uh, and at bottom are tensile forces. So this eccentricity help us, but at support this eccentric moment induced tensile stresses at the top fiber of the support section. However, since no external movement exists at the support point to balance these tensile forces, they can become excessively high. So therefore, we have to adjust the eccentricity of tendons at support. This is a technical point here. To control and limit these unwanted tensile stresses at support, the eccentricity is reduced near the support section. So this means that the tendon moves closer to the neutral axis at support section, reducing the tensile stress induced at the top fiber. So eccentric pre-stressing, here you can see we already discussed these calculations and we got these two equations. We already did this in previous video, and let's move to a basic concept method. A basic concept method tells us two types of sec tendon profile. Hop tendon profile. The change in eccentricity from the midspan to the support section is obtained by raising the pre-stressing tendon abruptly from the midspan to the support, a process called harping. Figure 1.3a shows a hard profile usually used for pre-tensioned beams and for concentrated transfer loads. Okay, draped tendon profile. The change in eccentricity from the midspan to the support section is obtained by raising the pre-stressing tendon gradually, gradually here in a parabolic form. This process is called draping. Figure 1.3b shows a draped tendon usually used in post-tensioning. Effective pre-stressing force PE, the pre-stressing force is stress equation would have to effective pre-stressing force if the total moment due to gravity is empty. When the moment is empty, MT means total moment, that is a moment due to self-weight plus a moment due to superimposed dead load, a moment due to live load. So when these total moments added, when these moments added, it becomes total moment, and in this case, the force will be PE, which we call effective pre-stressing force. In calculation, we will write it PE instead of PI. PI is initial pre-stressing force and PE is effective pre-stressing force. PE, and here you can see MT. When MT is used, then PE will also used in a calculation as PE is produced due to MT. The tensile stress in the concrete permitted permitted at extreme fibers of the section cannot exceed the maximum permissible in the code. Yes, tensile stresses limit for concrete. This is tensile stresses limit. So you have to check when finding a stresses. So we have to check. We will solve one numerical. In that numerical problem, you will clearly see we will use this check. We will use this code permissible limit. If it is exceeded, a bounded non-precedent proportion to the risk the total tensile force has to provide to control the cracking at surface load. Yes, definitely. If it exceeded, then we have to redesign it, and or otherwise we just say it is failed. Uh, in the next video, we will discuss C line method. So stay connected. Thank you.